Having me. I'm going to talk about some work that I'm doing with a student, Fikret Ceyhan, that will appear soon. And so let me begin with some apologies. Maybe you've heard a talk by me at an Int-from-Qubit meeting about the QNEC, about proving the QNEC. I'm sorry, here's another one. It's in some sense less general, although in some sense it's more general as well, so okay. You might want to hear about QNEC saturation. You might have heard of rumors of something called QNEC saturation. There's a very nice paper by Adam, Stefan, and Arvin showing this property about the quantum null energy condition in holographic theories. And with Srivatsan and Venn, we're working on trying to do this in general theories. Or at least general theories, general CFTs with a twist gap. This talk is not going to be about this because I'm going to be using algebraic quantum field theory methods which are sort of blind to the distinction between free theories and interacting theories, and this is very sensitive to that. So I will not talk about that. The other apology that I have is the title. So the title of the talk has recovering in it. And you might ask, why did I choose that name? Well, I chose that name because I think that there's a very interesting connection between what I'm going to tell you and something called a recovery map for quantum channels. However, we haven't really figured out that connection completely. It's still under construction. And we gave the title of the paper before we'd done the calculations, and the title stuck. Okay, so, but if you want to ask me about that at the end, then I can tell you something about that. Some things I'm not going to apologize about. We're going to present a mathematically rigorous proof of the quantum null energy condition in the context of algebraic quantum field theory. It's going to link two approaches to this question, one by Aaron Wall from, I guess, a year ago, or a little bit more, and then a proof that my group worked on. We will never mention the following words: replica trick, CFT, operator product expansion, local operator, entanglement entropy. Actually, we'll probably mention local operator, entanglement entropy. But roughly speaking, we won't. We will mention relative entropy, modular flow, and hopefully a little bit about the chaos bound. Okay. All right. So I have to start by talking about the setup. So the setup is algebraic quantum field theory. So we're going to talk about algebras associated to space-time regions. And here's some particularly nice space-time regions. They're just Rindler cuts. So I have my region that I'll call A, and then A primed is the commutative of A. So these are all somehow the operators that commute with these operators. So they're all space-like separated. So that's this green region. Now, given this setup, there's a particularly nice state in the quantum field theory. There's the vacuum state. It happens to be cyclic and separating, which is a nice property, but I won't define it. And given this, you can define these objects called modular operators. So there's some equation which it basically instructs you to solve this equation for these operators here, delta and J. J is some anti-unitary operator, and delta is this modular operator that I'll focus on. And this equation is true acting on states which you get, is defined with respect to the states that you get by acting with operators in the algebra of A on the vacuum. And if you're not familiar with this, we can write these things in terms of density matrices. So if you think of the Hilbert space as having some tensor factorization between the left and the right, then I can take my state, my vacuum state, and I can produce a density matrix for that. And then in the complement region, I can produce a density matrix. And then this modular operator is just some combination of those two density matrices, rho and the rho on the left, so which I'll call rho prime. It's sort of playing the role of the density matrix. So if we want to say something about things with a density matrix, then you can try to do it with the modular operators using this definition. And the other important thing for us is modular flow, which is some action on the operators in this algebra, which you just get by conjugating by these modular operators raised to the power is. And that action is always well defined. However, in quantum field theory, in this particular setup, vacuum and Rindler cut, it happens just to be a boost. Okay, so it's a boost that holds fixed this point here, which is, if you like, the entangling surface. And so it acts like this. Very good. J is just in this case, it's just CPT, where the parity operation is something that flips you between A and A prime. Okay, so now when we have these null cuts, there's another useful thing to do, and that is to translate them. So we're boosting things, so we can also imagine translating them. And now I'm going to translate them in a null direction. Okay, so this is my null direction, and I'm just going to move them like this. And then so I'm going to label them A with a little a subscript little a, and little a is just saying where I am along this line. And so there's some translation operator related to the null momentum, which moves you along here, and it acts on these algebras. So it takes one of these cuts. I'll call them cuts. I don't know why I do that, but I'll call them cuts, and it translates them. And similarly, there's a complement algebra, and you can act on them and translate them around as well. We can also boost them. We can also boost these algebras. So if I take the original modular operators I defined previously, which are defined with respect to the original cut here, then I can act on the algebra associated to this line here, this cut here, and I can boost it around. It moves up here, something like that. And so you get another algebra with just this boost factor. This 2 pi s is just the standard normalization that comes out from these definitions. And it turns out that you can also do another thing, which is calculate the difference in boosts. So if I have 2 boosts or 2 of these modular operators, I can calculate their difference for 2 different regions, A2 and A1, and their difference is just this null translation operator, this P, times A1 minus A2. And this structure is nice, and it's kind of obvious from quantum field theory. However, there's actually a very rigorous and formal structure behind it called half-sided modular inclusions. It was worked out by these people, and it's very, you don't really even have to say anything about quantum field theory. Yeah, so this structure sort of exists there, and actually this is the context in which we're going to try to prove the QNEC.
When you say you don't have to assume quantum field theory, you mean you don't have to assume boost or anything?
Yeah, so you just have some abstract definition about these modular operators that this is the important one. That this boost here acting on this modular action acting on this algebra takes you another algebra which is contained in the original one when S is positive. So if you have that, then you get all of this structure for free. So that's an obvious statement from quantum field theory point of view, but it's something you can just abstractly say, and that's what I mean.
So for this to apply, there has to be an operator P that...
No, you get P out of this. Yeah.
What's the definition of U? There is no P.
It's this. I mean, this is one way to do it. Take the difference of 2 modular operators under an inclusion like this. Yeah. So you get everything. You get you get the algebra that these operators satisfy. Okay. So this is kind of trivial in 2 dimensions, the pictures that I've drawn, but it turns out that something like this also works in higher dimensions, where I take a Rindler horizon like this, and I imagine cuts which are defined by some wiggly function. So that my wiggly function is A of y. Y is in this direction along this, say, entangling surface here. So this is, say, the entangling surface in high dimensions, and they have these wiggly functions. And it turns out that structure that I told you about also lives here, where I should think about the algebra of operators in some space-time region, which is determined by this picture. So by that I mean this is some null cut of the horizon, and you can associate to that null cut a space-time region. Right? This is just a codimension 1 region in space-time, but I can associate to that a space-time region, which is essentially the domain of dependence of this region, or if you like, it's the region that's space-like separated from the complement cut. Okay, so there's some, I'm not drawing it because it's very complicated to draw, but there's some space-time region and there's algebras associated to that. And I have exactly the same structure. So in particular, if I take this wiggly cut and I sort of scale it up, then I get some nested family of algebras, just like in the previous picture. I get some nested family of algebras just like this, and I get some null translation operator. However, now the null translation operator P is no longer very simple. It's not just it's not just the null momentum. It's some integral over the stress tensor times this modulating function. So integral t plus plus along this whole horizon with this modulating function. And so this is actually equivalent, P being positive, is equivalent to the average null energy condition in this context. And it follows here basically because of properties of modular Hamiltonians under inclusion. So while this is no longer a symmetry, it doesn't generate any symmetry, it's related to these modular operators in the same way as before, and so you can prove nice statements about it, like this positivity statement. So this is the context, the real context, but I'm going to draw pictures that look like this, just because they're easier to draw. Okay. Okay, so the quantum null energy condition. So the quantum null energy condition is usually motivated by the quantum focusing condition. So I'm going to go back to that. So the quantum focusing conjecture, quantum focusing conjecture is a conjecture about gravity, about maybe semi-classical gravity, or maybe more generally. But it's basically a statement about focusing instead of areas, you focus generalized areas. Or for, in terms of the entropy language, you talk about focusing of the generalized black hole entropy. So the generalized black hole entropy has two pieces. It has the Bekenstein-Hawking piece, as well as some entanglement entropy piece for the fields outside of the horizon. So I said entanglement entropy. So it turns out that for these null cuts and for small perturbations, say of the gravitational fluctuations around Minkowski space, you can show that this generalized area reduces to the relative entropy. Okay, so the relative entropy is some object that's defined in quantum information. I think I don't have to define it here. I will later. But it's something that compares some excited state psi, which you're interested in, with a vacuum. And it's defined with respect to the algebra for some particular cut, so it depends on this little a, and there's some constant here. Okay, then the focusing statement, in this case, when it reduces to this relative entropy, just becomes a statement about the second derivative of relative entropy. So my S of A is not entanglement entropy. It's going to be this relative entropy, which depends on this A parameter, which is labeling which cut I'm on. And so the quantum null energy condition, which derives from this quantum focusing conjecture, is a statement about quantum field theory, and it's just a statement in this context completely about the second derivative of the relative entropy being positive. Okay. Now, yeah, okay. So our goal is to prove this. So that's what I'm going to talk about. Usually when you talk about the quantum null energy condition, then you say something about the stress tensor, T++. I talked about a local operator. You say something about the stress tensor. Here I'm hiding all of that in this relative entropy. Okay, this is a better definition because in algebraic quantum field theory, it's harder to define, sometimes impossible to define entanglement entropy, and even T++ is also not usually mentioned. Okay, so now we have some statement about relative entropies that we'd like to prove. So let's just try to understand some typical relative entropies. So here's a picture of relative entropies in this context for these cuts. So A is this parameter here that I'm just drawing along here. And I've drawn two things. I've drawn the derivative of the relative entropy minus the derivative of the relative entropy for these purple regions. That's this plot here. And then I've also drawn the derivative of the commutant or the complement relative entropies for the region to the left, which are these green regions. Okay, so there's some function I can define here for these relative entropies with respect to the commutant algebras. And then you can sort of guess that it has to have this kind of structure. I've already built in the quantum null energy condition, right? So that's the statement that the second derivative is positive, so minus this, so then this derivative should be negative, right? So this should be monotonically decreasing, and this should be monotonically increasing. I've built in monotonicity. So monotonicity of relative entropy is standard. It's just a statement about the first derivative of relative entropy. And in this case, it's a statement about minus the first derivative of relative entropy being positive. And so that's the fact that these curves are all above the zero axis here. Okay, and so you also have monotonicity for this guy as well. Okay, yeah.
Want to say something about psi, or it's not important?
Oh, like what? So psi is the state that I'm working with.
What should I have in the back of my head?
Anything. It's a global state. Take it to be a global state for now. So it's a pure global state. It doesn't really matter for the argument, but let's just do that. Okay. Okay, so one feature that I've built into this is actually a sum rule that this satisfies. And this sum rule is sort of well known. It says that the change in, minus the change in relative entropy plus the change in the complement relative entropy is related to the null energy of this state. So p psi is just the expectation value of p in the state psi. And this is something, you know, this is an equation that has featured a lot. It's well known. Basically, you derive it by plugging in. Like, one way to derive it is to use these density matrices. You plug in the form of the relative entropy. This is the relative entropy. You put it in here, you get a lot of cancellations. At the end of the day, you're left with the expectation value of these full modular operators. And the modular operators, which include rho and rho bar, so and the commutant density matrix. And this difference, remember, is the null energy, right? That came from this half-sided modular inclusion business. So that's why you get the null energy on the right. Now, it turns out, interestingly, this was one of the hardest things for us to derive in this paper. So this is kind of taken as standard. However, it's kind of hard to derive in algebraic quantum field theory. And there's some technical reasons for that. So basically, if you assume that all of the relative entropies are finite, then it's easy to derive. But we didn't want to assume that, so it was actually hard to derive.
Why do you think it was important to not assume that?
Later on, I'm going to make statements about relative entropy of some state that I construct that I don't know has finite complement relative entropy. And so I want to use this equation to derive that fact, that it has finite complement relative entropy. This is a little too technical, but I can explain it later. Okay, so this equation, if I just take, you know, A1 to A2 to A, then this just becomes two derivatives. And so then this is some sum rule for these two things. They have to add up to a constant. And so I've built that into this plot. Yes? I'm going to work with the pure state, but you can sort of always work with the pure state because I'm interested in physics in some region. So I can always pick a state which is pure. Oh yeah, so this picture assumes purity, but when I make statements, when I'm trying to prove the QNEC, it won't matter. Yes. Okay, so the main result is to prove this statement. So the statement is a new way to calculate the minus the derivative of relative entropy. Actually, it was conjectured by Aaron. This is Aaron's paper. It's often called the ant proof. It was just a conjecture, and I've written it in a slightly different form, but in a form that's convenient for algebraic quantum field theory. So the idea is you define a quantity which I'll call M, which is a minimization over the null energy of possible purifications of the state psi. So what do I mean by purifications? I mean, take psi, which is a global state, but say I only care about it for the algebra A little a. Then I can act with some unitary on the complement algebra, and then it won't change anything in that algebra, in the original algebra. So it will agree with the original state psi for all one-point functions of operators in AA. However, it disagrees on the complement. So I can act with arbitrary unitaries from the complement, and then I minimize over that of the null energy. And the claim is that this is equal to minus the derivative of relative entropy. There's some technical condition here related to your question. So you have to assume that the complement relative entropies are also finite. This statement, which is a new way to calculate relative entropy, by the way, proves the QNEC sort of obviously, because if I have two regions, A1 and A2, then if A1 is less than A2, the minimization is over a restricted set of unitaries, because always unitaries acting on the complement, and the complement region is smaller if A1 is smaller than A2. So that means that the minimization will be bigger if I'm minimizing over less stuff. And so then this just becomes a statement about the second derivative of relative entropy being positive. Okay. All right. So if I can prove this, then that proves the QNEC. This was the content of Aaron's paper, essentially. He gave some reasons why you should believe this is true, which were pretty good. Okay, so how are we going to prove this? So we're going to prove it using some kind of sandwiching argument. So the idea is that there's an obvious bound. So for any purification P, I'm going to use the language purification. I apologize for that. So for any purification P psi, then that purification satisfies this sum rule for the derivatives of relative entropy. However, this derivative of that purification is just equal to the derivative of the original relative entropy, just because they have to agree in that case. And this derivative is always positive. So that means that there's a bound. I can show that m is always bigger than minus the derivative of the relative entropy. The challenge is to show that this is saturated. So I have to find some minimizing state, some optimal state, which has null energy equal to this. And if I show that, to minus the derivative of relative entropy, then I can sandwich m between these two quantities, and so that means that m is equal to minus the derivative of relative entropy. Yeah?
In which part of this argument are you using the fact it's a null cut as opposed to a space like that?
Everything. I mean, this equation, half-sided modular inclusions, yeah. So yeah, a lot.
Aaron had his argument for a special cut as well.
Yeah. So then this is not positive. I don't know. Yeah, it doesn't work, as far as I'm aware. We can talk about it though. Yes.
This purification will have the property that the state, by taking a small square of size delta A of the complement, you don't get any additional information about the state. Is that right?
I'm going to show you exactly what properties this has. Yeah. I mean, yeah. To motivate the solution to this problem, let's go back to the definition of relative entropy. So relative entropy in algebraic quantum field theory is defined in terms of something called the relative modular operator, which has a very similar equation that defined the modular operators for the vacuum. However, now I have some equation which relates the algebra acting on psi to some state where alpha acting on psi to alpha dagger acting on the vacuum. So it takes something acting on psi to something acting on the vacuum, and so that's why it's relative, because those states are different. So this defines these two operators. Actually, a fun fact, you can actually define this even when psi is not cyclic and separating. It's just annoying. In terms of density matrices, the relative modular operator is it's like before, we had a density matrix on the right and a density matrix on the left. However, now we have the vacuum on the right, and on the left we have the complement density matrix for psi. And then, this definition of relative entropy is just the expectation value of the log of this relative modular operator. And this agrees with the original definition after you use this fact, at least for this tensor factorization, that basically acting on the state psi with the density matrix for the state psi, I can always pass that function to the left, from the right to the left, as now a function of the complement density matrix. And you can justify this equation with a Schmidt decomposition. Okay, so now now, given this relative modular operator, we can talk about relative modular flows. So this is my favorite subject, so I'm very happy to talk about it. So the idea is we have this modular operator, so we can raise it to the power is, and we can consider a state. We're going to take the complement relative modular operator, so that's defined for the complement algebra, so alpha here, I didn't say it, is in the algebra A, and here alpha would be in the complement, or the commutant. So this is an interesting class of states, I claim, and what I'm going to claim is that these are the states that saturate the bound. Some intuition about these states is if I write it out in terms of density matrices, then I have the two density matrices here, but then I can use this fact that I can take this density matrix rho psi acting on psi and push it to the complement region. And then the end result is some unitary acting in the complement only. So this is an example of one of those purifications. So this does at least feature in that minimization, right? So it's one of these phi's. Technically, this is something called the Cartan cocycle, and yeah, there's a whole theory behind it. Okay, so I'm going to state this as a lemma. So I claim that this state, well, it certainly features in the minimization that defines M of A, but I also claim that you can calculate the null energy of this state. So you can calculate the null energy of this state, and it takes this form. It's minus the derivative of relative entropy plus e to the minus 2 pi s, this boost factor, times the derivative of the complement relative entropy. And so now you see, very simply, if I take s very large, this goes away, and I have a state which has the right null energy, minus the derivative of relative entropy. In particular, m is now less than this infimum over this set of states, which is then minus the derivative of relative entropy, and then so this gives you the sandwiching argument. Okay, so now to get to this is kind of the non-trivial thing. To get to this, in this talk, I'm going to go and talk a little bit more about the relative entropies of this state. So, we had pictures of the relative entropies, say, for this state psi. Now I'd like to understand what are the relative entropies, these S bar of A functions, for this new state psi s. And so let's develop a little bit of intuition for this state. So if you consider the one-point functions of operators in these algebras in this state, if I consider the one-point functions of operators in A, because this is a unitary, you can write it as a unitary acting on the left. It turns out that the one-point functions of operators in A are completely unaffected. Okay, that's what we expect for some purification. However, on the left, the operators in A prime pick up, you can show, using this sort of idea of pushing the density matrix from the left to the right, you can show that this picks up a boost. So all the one-point functions in the new state get boosted. So this operator gets, essentially flowed along, you pick up this vacuum modular flow, which is just a boost. So you might say, well, this is some kind of weird state where you're boosting one side and not boosting the other side, so maybe you would guess that the null energy is infinite. Yes?
So now we're looking at the unitary we're thinking about, is this a Cohn cocycle or is it a relative modular flow?
No, it's the Cohn cocycle.
It will not be geometric, right? Because vacuum has geometric action, but the excited state doesn't.
Vacuum has geometry. No, but it cancels here. So if I'm just interested in one-point functions of the complement, then it is geometric. It's not geometric up here, for sure. And that's kind of part of the complication. But yeah, this is a true fact about flow. So this is the same as flowing with the relative modular Hamiltonian, which then just gives you the boost. Because everything is acting on psi here, remember? Okay. So good. So you get this sort of half-sided boosted state. And so that sort of motivates what the relative entropies should be. So the relative entropies of this new state, which I'll call S subscript little s, that's going to be annoying, as a function of A, is this relative entropy here. And over here, because the one-point functions were unchanged, the relative entropy over here is unchanged. However, because the one-point functions suffer a boost, and that boost acts geometrically on the algebras, then you can show that the relative entropy of the boosted state for the complement region just picks up this boost factor. Now, this is only true if A is positive, and this is only true if A is negative, right? However, there's a whole bunch of null cuts that I haven't talked about. So the green null cut here, or the purple null cut here, and we haven't predicted the relative entropy for those. However, it turns out if you know the null energy of this new state, then you know everything because of this sum rule. Okay, so this sum rule allows you to take, basically you take A1 and A2 to be 0, which is where I'm applying this boost. Sorry, I should have said that. I'm applying this modular flow about 0. Then you take A1 to be 0, and you know those relative entropies, and then you know one of the other ones, and then from that you can predict the fourth one. Okay, so with that, and the form of the null energy that I gave you already, I just quoted this answer from this lemma, then you get these pictures, which are kind of interesting for the relative entropy of this new state. So let me explain these. So, okay, so let's focus on this. This is minus the derivative of the relative entropy of the right region as a function of A. So black is the input curve. So that's the relative entropy that I've of psi to begin with. That's just a cartoon. I just picked a random curve. Now what happens when you apply this boost is that if S goes very large and positive, this relative entropy pancakes down here to that constant that we're looking for. And if S is negative, then actually the relative entropy becomes very large over here. The derivative of relative entropy becomes very large. Now, if you look at the complement relative entropy, you notice that what happens is, as S goes to infinity, the complement relative entropy approaches 0, which means that the relative entropy approaches 0. So the complement region is somehow approaching the vacuum. So we're boosting the complement region, and essentially we're diluting everything, and it's becoming the vacuum. Okay. Okay. So that was assuming this result of this lemma. So how do we prove this lemma? So here's a wrong argument. So we have this sum rule. This is true, this sum rule here. So it's the sum rule for the null energy written in terms of the derivatives of relative entropies. And in some sense, I've told you what these are, right? I told you on the left, I know how to compute the relative entropy. Because it's a boost. On the right, I know how to compute the relative entropy. So I should be able to compute the relative entropy exactly at the origin. But then you remember these are actually derivatives of relative entropy. And the derivative can easily have a discontinuity, or it can just not be well defined. So you have to account for that possibility. The other thing you have to account for is that this equation assumes that the null energy of that state of psi s is finite. But that's just a guess, right? Who knows? It may be infinite. So there's a few things. So we need a different argument. And this is the argument that we came up with. Okay, so it turns out after some work, you can take PS. This is the expectation value of the null energy in this state. And you can analytically continue the S parameter. So you can analytically continue it into the strip, which goes from the imaginary part of S goes from -1/2 to 1/2. Furthermore, you can prove that it's periodic. So if I shift S by I, if I go from one side of the strip to the other side of the strip, I get back to myself. And it satisfies a bound on its growth. So the imaginary part of PZ, so I rewrite it in terms of Z because of this periodicity, where Z is e to the minus 2 pi S. And it satisfies this bound. In the upper half plane, its imaginary part is positive. Lower half plane, it's bounded by this. Actually, if you think about this for long enough, the only thing that satisfies this is an entire function of Z. And actually, it's just a linear polynomial in Z. So once you prove these various things, you know the form of the null energy. It's just some constant, R, plus Z, which was e to the minus 2 pi S. So remember, it was a polynomial in Z, a linear polynomial in Z. And then it has to be p psi minus r here, because when I set S to 0, I have to get back to the original null energy. Okay, so this argument doesn't actually fix r, it's just some constant. But it turns out that this form is sufficient. If I know this form of the relative entropy, then I can go and calculate those functions that I told you about before. I use monotonicity on those functions, which we know is true. to prove that R is equal to minus the derivative, which then proves this answer. And this answer is somehow, I think at least, it's some version of saturation of the chaos bound. And I think there's some relation to ADS-CFT. Maybe I won't say much about that now. Maybe I can comment on that later. Good. Okay, so who wants more details? I'm going to give more details. Sorry. Okay, so in reality, we can't really talk about or easily talk about the expectation value of this operator because it's an unbounded operator. So what we do is we think instead about this translation operator. So e to the I a p. And this defines some function. So it's a function which is the expectation value of this operator, essentially. And it depends on two complex, potentially complex numbers, s and eta. Eta is just rewriting a as e to the 2 pi eta times some constant epsilon. And so our goal is to take this limit. Epsilon goes to 0. If I can take that limit, then this answer is just the null energy of that state. Okay. Some more technical details. We first prove this. So actually, we only prove these statements for a special class of states. So these statements, which are called entire states. So these are states which you get by essentially, which have bounded spectral support for P, for this null energy operator. And that means that this vector in the Hilbert space is essentially an entire function, a vector-valued entire function in the complex A plane. Okay, so this is a nice set of states, and it turns out you can approximate any state by this, and then you just have to make some continuity argument, which we managed to use to get the general answer. Okay, so the goal then is to find an analytic continuation of this function, which is totally well defined, into the complex S and eta plane. Okay, more details. So we showed that this function can be analytically continued into this following tube region, complex tube region. So it's defined by the imaginary parts of these parameters S and eta. And so notice the imaginary part of S goes between -1/2 and 1/2. But eta goes between, imaginary part of eta goes between 0 and 1/2. And then you sort of panel out this region with various analytic continuations, and then you patch them together. Okay. Good. So, okay, so there's a set of analytic vectors that you can define to each of these triangular regions. And you use this sort of ARAKI method to define these, which I first read about in Edward's paper in the appendix. And you show that these are all, you can define these vectors, they're analytic, they're holomorphic in this region, in these various regions, and they're norm bounded by 1. And then you can, with these, you can construct these functions. This function g of s, this analytic continuation. So notice it turns out that in this analytic continuation, you have this translation operator here, and it's an unbounded translation operator. So in the sense that it's sort of like e to the p times some number, and the real part of that number is positive, so it's unbounded. So the way to control that is to use this entire state. So this psi is a nice state, so that this makes sense. And given that, you can find this continuation here. It's not periodic. So this is not the same as this. However, okay, sorry. I'll get to that in a second. It turns out that analyticity allows you to establish this limit. There's a nice point here where you can prove monotonic convergence of this limit. And then you use some properties of families of analytic functions, which guarantees then this Vitali's theorem, which actually guarantees that if it converges in some point here, which is not just one point, it's a whole complex region, a whole one parameter region, then you can just show that it converges everywhere, which is kind of a non-trivial statement, but you can, that's good. And the bound that I quoted comes from the bounds on these vectors. Periodicity, you construct two functions, you get another function which is periodic if I identify this, and so it's not periodic, but it's defined such that if I identify this and this, it's continuous over here. So if I go over here, I come back over here, but now there's a branch cut in the middle here. And then you show in this limit that we're trying to take, these functions are the same. And so that actually establishes periodicity, because then I can go here and then pass over here and go here. Okay, so we're done. I'm a bit early. Yeah, okay. No, I'm not early. No. Great. Okay, so that was the proof. I hope you got a flavor of it. So basically, we've proved a new formula. I think the most interesting thing is we've proved a new formula, which was conjectured by Aaron, for computing derivatives of relative entropy in terms of just a variational expression over the null energy. Okay, so I think that's interesting. I'm sure there's lots of applications. I can imagine lots of applications of this. One interesting thing is to understand what is this in ADS-CFT. We can also connect back to this previous work that I did with Srivatsan, Zuhair, and Khwaja on proving the quantum null energy condition. We wrote down some pretty weird correlation functions and extracted it from that. It turns out that you can just construct a state, the correlation functions of which are the same as this paper, and the null energy you can just now calculate. And it takes this form, and at large S, it just projects onto the quantum null energy condition. So positivity of the ANEC in this state just becomes the QNEC. So that's what I mean by recovering the QNEC from the ANEC. So the QNEC is just the ANEC in a different state. Okay. Okay, some discussion points. Yeah, I only touched the surface of this powerful method, but maybe you can use it to improve, make some improvements on the QNEC. I think there's something interesting about bulk reconstruction that I'll say. Maybe this is crazy, but I like this idea of this periodicity under this S goes to S plus I. And somehow I'd like to relate that to the chaos bound and saturation of the chaos bound. Because essentially when you saturate the chaos bound, you're getting a periodic function like this. And so, another way to get that is just to demand that it's true. And this I think is kind of a weak form of a gap in anomalous dimensions. So maybe if you study these correlation functions where it's not necessarily periodic, here we proved that it was periodic, but maybe you study these modular flow operators where it's not necessarily periodic, but then you put in that assumption, then what can you derive from that? Maybe you can derive some interesting things about ADS-CFT. And then the final point is, can we understand this in terms of recovery maps? I'm not going to say anything about that. I'm not really qualified at this point, but I'm sure that there's a very interesting connection there that if anyone wants to talk with me about it afterwards, I'd be happy to do that. Okay, let me finish.